today we will discuss about some very simple block codes. So, this is the outline of today's talk. Before I discuss some examples of linear block code, I will first describe what do I mean by dual of a code, and then I will move on and describe some very simple linear block codes such as repetition code, single parity check code, Hamming code. So, before I discuss what is dual code, I would like to define what do I mean by two vectors u and v being orthogonal. So, two vectors u and v are orthogonal if their inner product, which is defined like this. So, component wise dot product, if that inner product is 0, we call these n tuples u and v as orthogonal. So, for a binary linear nk code, its dual has the parameter n and n minus k, and it has the following properties. So, a dual code is defined such that its set of code words v are orthogonal to the set of code words of the original code C. So, if v is a code word which belongs to the dual of a code C, then v would be orthogonal to code words u which belong to the original code C. We can show that for a linear block code C, the dual code is also a linear code. So, let us take x and y to code words which belong to this dual code of C, which we are denoting by CD. Sometimes people use this notation also for the dual. Now, if x and y belongs to the dual code, then we know that any code words belonging to the dual code, they are orthogonal to the code words in the original code C. So, if u belongs to C and x belongs to dual code C of D, then x dot u will be 0, because the code word x is orthogonal to code word u. Similarly, code word y which belongs to the dual code and code word u which belongs to the original code u, since they are orthogonal, their dot product will be 0. So, we can write x dot u is equal to y dot u is equal to 0. This follows from the property that a code which belongs to the dual code is orthogonal to the code words in the original code C. So, then for some binary lambda and mu, we can write this lambda x plus mu times y dot product with u as lambda times x dot mu plus mu times lambda dot u. Now, what is x dot u? Now, x dot u is 0 because x belongs to the dual code and u belongs to the original code C. So, they are orthogonal, that is why x dot u is 0. Similarly, y dot u is also 0. Hence, we can write lambda x plus mu y dot product with the code u is also 0. So, we have shown basically this belongs to the dual code. So, we have shown that if our original code linear block code is original block nk code is linear, the dual code is also linear. And why does this belong to the dual code? That is because this is orthogonal to the code word which belongs to the u belongs to C, and since this is orthogonal to a code word which belongs to C, so this must belong to the dual code. The next property that we are going to show is if we have a linear block code, we denote it by C, whose generator matrix is given by this capital G, and if X belongs to the dual code of this original code C. So, the claim that we are making is, if X belongs to the dual code, then this relation holds, and if this relation holds, X belongs to the dual code. That is what we mean by if and only if. So, if X belongs to the dual code, then X G transpose should be 0, and if X G transpose is 0, X should belong to the dual code. So, we are going to prove that if X belongs to dual code, then this relation holds, and further we will show if this condition holds, then X will belong to the dual code. So, let us write the generator matrix of a linear block code C. As you know, this is a K cross N matrix, and this G0, G1, G2, Gk minus 1 are these K generators, each of length up to L. These are length L. So, this G is K cross N matrix, and any code word can be generated using these generators G0, G1, G2, Gk minus 1. Now, Xg transpose is basically given by inner product of X with G0, X with G1, X with G2 up to X with Gk minus 1. Now, what happens if X belongs to the dual code? If X belongs to the dual code, then set of code words which belongs to the dual code, they are orthogonal to the set of code words which belongs to the original code C. Now, we know that if X belongs to the dual code, then X, inner product of X with Gi should be 0. Why? Because the original code is generated using these generator sequences G1, G2, Gk minus 1. Any linear combination of this G0, G1, G2, Gk minus 1 will give me my coded sequence. V is, you can write G0, G0 plus dot 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 Uk minus 1, Gk minus 1, right. So, if X belongs to the dual code, then inner product of X with Gi's would be 0, and hence Xg transpose will be 0. So, what we have shown is, if X belongs to the dual code, from the property that the code words in the dual code and code words in the original codes, they are orthogonal to each other. From that property, we get this condition that inner product of X with Gi's will be 0, or in matrix form we can then write, because X, inner product of X with Gi's is nothing but Xg transpose. So, then Xg transpose would be 0. Next, we are going to show if Xg transpose is 0, then X must belong to the dual code. Now, if Xg transpose is 0, then this condition holds, that inner product of X with Gi is 0 for I equal to 0 to k minus 1. Now, what is a code word? A code word is obtained by linear combinations of these generators G0, G1, G2, Gk minus 1. So, if C belongs to the linear block code C, then C is essentially generated by linear combinations of these generator sequences, where these lambda i's are zeros and ones, because we are talking about binary codes. Now, note, what do we want to show? We want to show if Xg transpose is 0, then X must belong to the dual code. And when will X belongs to dual code? We have to show that a code word which belongs to original linear block code C and set of code words which belong to the dual code, they are orthogonal to each other, or in other words, their dot product is 0. So, let us take a dot product this is X which you want to show that it belongs to the dual code, and C is a code word in original code C. So, what is X dot C? X dot C can be written as X dot summation lambda I G I. This I can write as summation over I lambda I X I dot G I. And what do I know from this condition? That X G transpose is 0. I know from this condition that inner product of X with G I is 0. So, that means this term is equal to 0. Then what I have shown? I have shown that X dot C is equal to 0. That means X and C are orthogonal to each other. So, if C belongs to the original code, this capital C, then X must belong to the dual code of this code C. So, hence we have shown that X belongs to the dual code of C. Now, we also know that if X belongs to a particular code, let us say dual code, then we know the condition that if for any valid code word, we know that let us say X is a valid code word, then we know this property holds, that code word paradigmatic matrix transform is basically equal to 0. So, if we compare this form with this, you can immediately guess that the generator matrix for the dual code is given by the parity check matrix of the original linear block code C, and the parity check matrix of the dual code is given by this generator matrix of the original code C. So, this is what I am saying here. The generator matrix G of a linear block code is the parity check matrix for the dual code and vice versa. Okay. Now, what is a self dual code? If a linear block code is equal to its dual code, then it is called a self dual code. So, as you can make out, the rate for a self dual code should be half, because k should be n by 2. So, n is always even for a self dual code, and the dimension of the code is always n by 2. An example of self dual code is 2412 Golay code. Okay. Now that we have defined dual code, let us now come to the other topic, which is some examples of linear block codes. So, a very simple example is the repetition code. So, if for repetition code k is 1, and let us say we have a rate 1 by n repetition code. So, the code word length is n, there is 1 input bit and n outputs. And how is repetition codes generated? So, we repeat the same information n times. So, for a binary repetition code, it will have 2 code words, 0 and 1. So, if the information bit is 0, the output will be all zeros repeated n times, and if the input is 1, this will be output will be all 1 repeated n times. So, there are only 2 code words in our repetition code. So, we can then write down our generator matrix. How is generator matrix? If V is the coded sequence, U is the information sequence, then generator matrix, they are related to generator matrix in this particular way. So, since our output is the bit repeated n time, the generator matrix for repetition code will be all ones. So, this is 1 cross n. Now, how do we decode a code which is encoded using repetition code? So, what we do is we take a majority decision. So, let us say For 0 we are sending n zeros, and for 1 we are sending n ones. So, at the receiver, when some of the bits get flipped or they are changed, what do we notice is we look at block of n bits and we see what is the majority, is it 0 or 1. If it is 0, majority of the bits are 0, we decide in favor of 0. If it is 1, we decide in favor of 1. And we can see the minimum distance of this code is n, because there are only 2 code words, all 0 code word and all 1's code word. So, it can correct n minus 1 by 2 floor of that. It can correct so many errors, and it can detect n minus 1 errors. Because any error pattern of weight less than n would not change it into any valid code word. So, all error patterns up to weight n minus 1 can be detected by this repetition code. Let us look at another example of a linear block code. This is single parity check code. As the name suggests, we are adding one single parity check bit. So, the information sequence length is k, and n here is given by k plus 1. And how do we generate this single parity check bit? This is as follows. So, if your information sequence is given by this, so you have a k bit information sequence, let us call it u0, u1, u2, uk minus 1, then we generate this additional parity bit in this fashion. So, p is equal to u0 plus u1 plus u2 up to uk minus 1. So, in other words, if information sequence is even parity, that means sum of them basically add up to 0, then p will be 0, or else if the information sequence has odd parity, p will be 1. So, as you can make out, this single parity check code will always have even weight code words. So, each code word I can write in this particular fashion. So, I have these k information bits and one parity bit. So, I can write the same thing in the form of a generator matrix. As we know, our coded sequence can be written as input times generator matrix. So, you can see first bit is a parity bit, which is sum of all ui's. So, first column will be all ones, and then this will be a identity matrix, because the second bit is u0, third bit is u1, u2 and so on. So, this is a identity matrix. Okay. Now, we can write down the parity check matrix for this also. As you can see, this generator matrix is in systematic form. So, what would be the corresponding? This is of the form like this. I have P I. So, parity check matrix will be I P transpose, right. So, what I have here is, this is my P transpose and this is my I. This part is my P and this part is my I. So, parity check matrix will be I P transpose. So, that is this. As I mentioned, a very interesting property of single parity check codes, all code words of single parity check codes are of even weight. And we can see the minimum distance of the code is 2. A simple, very simple way to check is, look at the columns of the parity check matrix, what is the minimum number of columns that add up to 0? In this case 2. Any 2 columns will add up to 0. So, the minimum distance of this code is 2. Now, since all code words have even weight, any odd error pattern can be detected by single parity check code, because any odd pattern, any odd weight pattern is not a valid code word. So, a single parity check code can detect all error patterns which has even number of errors or odd numbers of errors, right. So, as long as error pattern has odd weight, single parity check code can detect it. And it is not very difficult to see that single parity check code and repetition codes are dual to each other. You can see basically the parity check matrix of single parity check code is same as generator matrix of the repetition code, and similarly the parity check matrix of repetition code is same as the generator matrix of the single parity check code. And you can check the dimensions of the single parity check code is n minus 1 and this dimension is 1. So, single parity check code and repetition codes are dual to each other. Next we consider Hamming codes. So, Hamming codes are single error correcting codes. These are single error correcting codes and they are described by these parameters. So, for any m greater than equal to 3, the code word length is given by this. The number of parity bits is equal to m. So, number of information bits are n minus k, n minus m. So, this is 2 to the power m minus 1. So, these my number of information bits. It has minimum distance of 3. So, it can correct single error and it can detect 2 errors. So, how do we describe Hamming code? We can describe the Hamming code by generator matrix or the parity check matrix. So, a parity check matrix of a Hamming code consists of all non-zero m tuples. So, if the number of parity bits, as I said, is m, then code word length is 2 raised to the power m minus 1 and the entries in the parity check matrix are all non-zero m tuples. Now, how many m tuples do we have? We have total 2 raised to the power m tuples, and out of those, so these are like 0 0 0 0 0 1 and you can go on up to all ones, and this is m times m. Now, if we remove the all 0 1, so total number of non-zero m tuples is basically given by 2 raised to the power m minus 1. So, the columns of the parity check matrix of Hamming code are nothing but non-zero m tuples. So, there are total 2m of them, 2m minus 1 of them. Okay. And if we want to write the parity check matrix of a Hamming code in a systematic form, then we can write it in this way. So, parity check matrix will have an identity and then some matrix P. Since identity matrix will consist of all patterns, all m tuples of weight 1, PT should consist of all m tuples of weight more than 1. So, it consists of all m tuples of weight 2, 3, 4 up to m. So, let us take an example. Let us consider m equal to 3. So, if m equal to 3, we know n is 2 raised to the power m minus 1. So, the length of the block code in this case will be 7. Now, how many number of parity bits? Number of parity bits is given by m, so this will be 3. So, then what is the number of information bits? This is 7 minus 3, that is 4. So, this is a 7-4 code. Now, as I said, the parity check matrix consists of all non-zero m tuples. So, m here is 3. So, let us list all non-zero m tuples. So, we can write 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So, these are the 7 non-zero m tuples, right. And if you want to write your parity check matrix in a systematic form, what will you do? So, this is your I. So, I am writing these patterns which are like 1, 2 and 3. I am writing these patterns, and then what I write here is the other m tuples. So, you can see this is m tuple of weight 1, these 3 are m tuples of weight 1, and then this is a m tuple of weight 2, and this is m tuple of weight 3. Now, since this matrix is of the form I and P, I can write the generator matrix. This will be P transpose I. So, we can write this. So, P transpose, so 1011 will come here as 1011, 1110 will come as 1110, and 0111 will come as 0111. And then this is the identity matrix. So, this is our generator matrix for this 7-4 Hamming code. The point to be noted here is, once you fix your m, all other code parameters are fixed, n is fixed, right, because n is 2 raised to the power m minus 1 and number of parity bits is equal to m. So, for the Hamming code, once you fix m, the other parameters of the code are fixed. Now, let us see how we can correct errors using Hamming code. As we said, this has minimum distance 3, you can see here. So, let us take any 3 columns, let us just take this column, column number 1, column number 2 and column number 4. You can see column number 1, 2 and 4, they will add up to 0, 0, 0. So, 3, and that is the minimum number of columns that will add up to 0. So, which means the minimum distance of this code is 3. If the minimum distance of this code is 3, what is the error correcting capability of this code? It is d minus 1 by 2 floor of that, and this comes out to be 1. So, Hamming code can correct single error. So, let us see how we can use Hamming codes to correct single error. So, first thing what we will do is, we will rearrange the columns of the parity check matrix of Hamming code such that column in position I represent integer I. So, as we said, the parity check matrix of Hamming code are all non-zero m tuples. So, we will arrange them in such a way such that the ith column represent ith bit. Now, what do I mean by that? So, let us go back to our same example, m equal to 3. So, in this case n is equal to 7 and k is equal to 4. Now, note the way I have arranged this. So, this is my MSB and this is my LSB, least significant bit and the most significant bit. So, each column represents a number in this particular way. So, this is the least significant, this is the least significant bit, this is the most significant bit. So, this is 0 0 1, that is binary 1. So, this is my column number 1. This is 0 1 0, that is 2, 0 1 1, that is 3, this is 4, 5, 6, 7. So, note what I did was I rearranged the column of the parity check matrix of Hamming code such that now ith column represent ith number basically. So, column in ith position represent the integer I. Now, if I do that, then let us see how this helps us in locating the position of the error. So, let us say R is my received vector, this is my received n bit vector, and I am interested in knowing whether R is in error, and if R is in error, let us, because the single error correcting code, let us say a single error has happened, then I am interested in correcting this single error. So, what do we do? The first thing to find out whether error has occurred or not, first thing that we do is we compute the syndrome. How do you compute the syndrome? We take R H transpose, and what is our H? H is our matrix, this matrix which is arranged where the columns are arranged in such a way such that column in ith position represent integer I. So, since it is a single error correcting code, it can only correct at most one error. So, we assume let us say at most one error has occurred, at most. Of course, if there is no error, then syndrome would be an all 0 vector, and if a single error has happened, the syndrome would have been a non-zero vector. Now, what you will observe is if a single error happens, then that single error will be basically whatever is the syndrome, from there we can find out which bit location is in error. So, in case of Hamming code, if single error has happened and you have arranged your parity check matrix in such a way such that column in position I represent integer I, then the syndrome would be either 0 vector in case there is no error, or otherwise in case of single error it would be a column of this parity check matrix. So, when a single error happens, the number represented by the column of the calculated syndrome is the position in the code word where the error has happened. So, see, it is so nice. So, by looking at the syndrome and comparing it with the column of the parity check matrix, our reordered parity check matrix, we can find out the location where the error has happened. And since for a binary code, basically if we can locate the error, so the bit can be either 0 or 1. So, whatever the bit is, we just flip that bit and get our corrected code word. So, let us take an example. So, let us say this is a code word for this 7-4 Hamming code, and let us assume that there is a single error has happened and this bit got changed from 1 to 0. Now, given this received sequence, I am interested in finding out what is my estimated code word. First of all, I am interested in finding out whether an error has happened or not, and if the error has happened, I am interested in correcting that error. So, as I said, the first thing that I am going to do is I am going to compute the syndrome. So, what is my R? This is my R. And what is my H? H matrix is basically my parity check matrix of the Hamming code, where the columns are arranged in such a way that column in ith position represents ith integer. So, if we take H transpose, so we will get 1 0 0 0 1 0 1 1 0 0 0 1 1 0 1 0 1 1 1 1 1, right, and that is what I get here. So, this is my R, this is my H transpose. Now, H transpose, so this is 1 2 3, this row will participate, this row. So, my syndrome will be this plus this row plus this row. So, this will be 0 0 1 plus 0 1 1, which is 0 1 0. So, my syndrome here is 0 1 0. Now, what do? I go back and check which column is 0 1 0. So, if I go back to my parity check matrix, I notice that 0 1 0 is this second column of my parity check matrix, right. So, what does it indicate then? It indicates that the second bit of my code word is in error. So, then I can go ahead and correct this error. So, this second bit from the syndrome, I can find out that this syndrome is nothing but the column in the second location. So, my second bit is in error, and since we are talking about binary code, so then this 0 should have been 1. So, my estimated code word is then 0 1 0 1 0 1 0, and you can see that is what I had transmitted. This is the same code word that I have transmitted. You can yourself verify, change some other bit location, introduce some other single error, and you will see from the syndrome you can find out the location of your error. So, it has a very simple decoding algorithm. Now, as I said before, in case of Hamming codes, once I fix my M, my code parameters are fixed. So, for example, the examples that we were dealing with, we had taken M equal to 3. So, the moment I fix M equal to 3, my N is fixed, it is 2 raised to 3 minus 1, that is 7. So, K is 7 minus 3, that is 4. So, this becomes the 7-4 code, right. What if I am interested in designing, let us say 8-4 code, or let us say I am interested in 7-3 codes, 6-3 code. So, there are various techniques available to tweak the parameters of the code. We are going to talk about some of them. We are not exhaustively covering all possible ways of lengthening and shortening a code. We just give you just few examples to illustrate this idea of changing the parameters of the code. So, the first thing that we are considering is a shortened Hamming code. So, how do you get a shortened Hamming code? You delete L columns from the parity check matrix of your Hamming code. Now, if I delete L columns, that means my code word length is decreased by L. So, my new code word length is then 2m minus 1 minus L. So, this is my code word length. Now, number of rows are still the same, that is m. So, number of parity bits are still same, but since I deleted L coded bits, so number of information bits also got decreased by L. Now, minimum distance of a Hamming code is 3. If I am deleting some columns, then minimum distance cannot be less than what was the original minimum distance of the code. Why? Because you can see if I have a parity check matrix here, and let us say I have these columns, let us call it A1, A2, AN. Now, if I am removing some of the columns, I can carefully remove those columns which are causing the sum of, let us say, d columns to be linearly dependent. So, if I remove some of those columns, I can possibly increase my minimum distance, and that is why I wrote, by whenever you delete columns from the parity check matrix, the minimum distance is at least what was there in the original code. This is one example of a 7-4 Hamming code. So, if I delete, let us say I delete this, if I delete this column, what do I get? I get a shortened 6-3 Hamming code. So, when I delete this, my n becomes 6 from 7, and my information bits also reduce from 4 to 3. This code also has minimum distance 3. You can see 3 columns will add up to 0. Let us say this column, and this column add up to 0. So, minimum distance is still 3 for this code. So, whenever you want a shortened code, make sure you remove those columns in a judicial way, so that potentially you can increase the minimum distance. In this particular example, if I delete one column, I cannot increase the Hamming distance, but if I delete more columns from this parity check matrix, I can potentially increase the minimum distance of the code. Another class of code is what is called expurgated codes. So, what is expurgated Hamming code? So, if H is the parity check matrix of Hamming code, then I define a new parity check matrix which has all ones as the last row. Now, note, the parity check matrix of Hamming code does not have all ones. So, when I add an all one row, essentially the rank of this matrix will be 1 more than the rank of the original matrix H, because any linear combination of last row with the rows of the earlier parity check matrix H would not be dependent. Hence, the rank of this new matrix H1 is n minus k plus 1, and what is the number of columns of this matrix? That is n. So, rank of this matrix is n minus k plus 1, then what is the dimension of the null space of this, or what is the dimension of code sequence here? So, that is basically, this is n minus dimension of H matrix. So, that becomes k minus 1. So, the new code that we derived by adding an all one row in the parity check matrix of the Hamming code, we get a new code which is a n k minus 1 code, and this is known as expurgated Hamming code. Now, one of the interesting property of this code is, this code contains all even weight code word. It is not very difficult to prove. If V is a valid code word, then we know V H transpose should be 0, and last row of H1 has all ones. So, when we take transpose, so the first column will be all ones, and when we do V H1 transpose, what we will get is, let us say the components of V are V0, V1, V2. So, V n minus 1, then what you will get is basically some of these components of this code word, they should add up to 0, and this will happen only when V has even weight. So, this new code that we generated, expurgated code, is basically has all even weight code words. So, if you have an odd weight vector, then V H transpose cannot be 0, because of this all ones in the parity check matrix of this new matrix H1, expurgated code parity check matrix. Okay. So, V H1 transpose cannot be 0 if V has odd weight. So, you can see that this is one way of getting rid of odd code words. So, by adding an additional all 1 rows in the parity check matrix of the original code, we actually got rid of all odd weight code words. So, the minimum distance of this expurgated Hamming code would be then 4. Why? Original code has minimum distance 3, but now we got rid of all odd weight code words. So, the minimum distance of this new code, expurgated Hamming code, would be 4. So, minimum distance is 4. So, this is an example. This is the parity check matrix of the original Hamming code, and if we add all 1 rows in the parity check matrix, we get the parity check matrix of a expurgated code. Finally, I will conclude this lecture with another class, which is basically extension, which is called extension of a code. So, this is an example of an extended Hamming code. So, how do I generate an extended Hamming code? So, note, so this is the parity check matrix of my original Hamming code. I add an 0, so I add an additional column which is 0 here. So, these are all 0 here, and then I add 1 row which is all 1. Now, it is not very difficult to see that the rank of the matrix will be, if the rank of H is, let us say, n minus k, the rank of this matrix H1 will be n minus k plus 1, because the parity check matrix of the Hamming code did not have an all 1 row, and then these are all zeros and this is 1. So, any linear combination of this row with these rows basically would not change the, it would not decrease the Hamming distance essentially. So, this will have, the rank of this matrix will be 1 more than the rank of the original parity check matrix H. So, what we are saying then is all rows of these parity check matrix H1 are linearly independent. As I said, that is because original H matrix did not have all 1s here, and this is 1 here, this is 0 here. So, if we take linear combinations of this with any of the rows of the original parity check matrix, they would not be linearly dependent. So, all rows are linearly independent, hence the rank of this matrix is n minus k plus 1. And what is the number of columns? The original matrix had n columns, and we added 1 column, 1 more column. So, number of columns here is n plus 1. So, this will define a code of length n plus 1. So, then we can find out what is the dimension of null space, or so this is number of coded bits, this is the rank of the new parity check matrix. So, number of coded, so the dimension of null space is k. So, this will then generate an n plus 1 k linear block code, and this is known as extension code or extended Hamming code. If this H is a matrix, a parity check matrix of Hamming code, the code described by H1, which is given by this, would be extended Hamming code. And again we can see that the extended Hamming code will have only even code words. That is because the last row of the parity check matrix contains all 1s. So, V H transpose cannot be 0 if V has odd weight. So, the minimum distance of extended Hamming code is 4. Now, please note that some of the techniques that we mentioned here, extension, shortening, expurgated, that is valid for any other linear block codes too. And these are some of the ways in which we can change the code parameters. So, with this we conclude this lecture. Thank you.